All right, so the last thing we're going to do with these exponential models here is just look at an application problem in order to model this situation. So what it tells us is the half-life of a substance is 20 years. If we start with 100 grams of the substance, how much will remain after 150 years? Okay, so kind of the thoughts that you should be thinking about as you read through a problem like this is, do you see the three required numbers for the function? Okay, so in this case, if we look at this, so it says our half-life is 20 years. So that's how long it takes for this substance to be cut in half. So that's going to be our T value. Our T would be 20 on here. We start with 100 grams. Okay, our starting value is always our A. Okay. And because we are looking at a half-life, that tells us that our base would be equal to 1/2. So you could kind of put that together and build your equation here, 100 times 1/2 to the power of x over 20. And from there, you could actually answer the question of how much will remain after 150 years by just plugging 150 in for your x and solving for your y, okay? So whenever you're looking at one of these application problems, you want to start by identifying those three required numbers. You want to find your starting value. You need to find what's your growth or decay rate, and then how long does it take in order to grow or decay by that rate. Okay. All right, so here, if we look at example 3, it says the population of a certain town triples every 37 years. If there were 27,000 people in 2014, how many people will live in the town in the year 2020 and the year 2050? Okay, so we have to start by thinking about identifying our three important numbers. So remember, our equation is y is equal to a times b to the power of x over t. So a is our starting value, b is our growth rate, and t is the amount of time that it takes to grow by that rate. Okay, so if we read back through this, it says the population of a certain town triples. Okay, that's telling us how our population is growing. So triples would be our b value. So if something is tripling, that means it's multiplied by 3. Okay, so our b value is 3. Right. Now it says it triples every 37 years. So that's the amount of time that it takes to grow by that rate. So that would be our t. So t is 37, right? And it says if there are 27,000 people in 2014, okay, so this 27,000 is going to be our starting value, which is our A. Okay, so let's go ahead and put this all together into an equation. So we're going to have A, or y is equal to 27,000 times 3 to the power of x over 37. Okay, now it's always a good idea to make a note about what your variables are representing. So in this case, x is going to be the years since, in this case, 2014, because that's the year that our starting value corresponded to, 3 years since 2014, and our y is going to be the population of the town. Okay, all right, so now we can actually answer the question. So you always have to build your model before you can answer any questions about it. So we want to know how many people will live in the town in the year 2020 and in the year 2050. So let's start with 2020. Okay, So in order to figure out the x value we plug in, we just have to keep in mind that we're going from 2014. So from 2014 to 2020, we have 6 years. So we're going to plug in x equals 6. So y would equal 27,000 times 3 to the power of 6 over 37. Right, and then I'll just need to pull out my calculator. So 27,000 times 3 to the power of 6 over 37. So we have 32,265.23. Now we're talking about population of a town, so we're talking about a number of people. Definitely don't want to have a portion of a person, so we're just going to round it. So since it's 0.23, I'm going to round down to 32,265 people. Okay, so in the year 2020, there would be 32,265 people in this town, okay, according to this model. Okay, now we saw previously that sometimes these models can break down, but 2020 is pretty close to the initial data of the 2014, so I think our model is probably still going to hold up in that amount of time. All right, and then let's see about 2050. So if you need to, you can calculate the amount of time. So 2050 minus, again, our starting year of 2014. You're always thinking back to when did your data start? We always go back to that 2014 for this model. So it would be a 36. So our y would equal 27,000 times 3 to the power of 36 over 37. So you see, remember, our tripling time was 37 years. We've gone 36 years, so we've almost tripled. We can kind of see that in a second here. So 27,000 times 3 to the power of 36 over 37. Again, we're going to round this. So we'd have 78,630, and it's a 0.28, so I'm just rounding down to 630. So 78,630 people. Okay. Now again, I just kind of want to look at this. So like I mentioned, 36 years is almost our tripling time. So let's see how close we were to tripling there. So if we took this 78,630 number and we divided it by the original 27,000 and get 2.9. So you can see that it's almost tripled the original population of the town because you've almost gone that full 37 years. All right, guys, so that is it for our 3.3.